Good morning, everyone. So, Mike Gladders and I are going to talk about optical cluster search. The primary topic area will be strong lensing. So, what we thought we'd do is we'll divide our talk into two parts. I will sort of give a general overview of the RCS, and then Mike will talk about the RCS2 new result in strong lensing that we have. Now, unfortunately, I had to give you a version of the talk that's from last night rather than from this morning because I lost my cursor when I plugged it in and I forced to reboot, and I realized I did not save my latest version. So you see that there will be things that will be missing, but mostly words, not any plots that I'm going to describe to you by words. This is just a list of the RCS2 collaborator, a bunch of people from many places. Many of them have been in Toronto at one time or another. So we do cluster survey. Mike and I spent the last 10 years doing that, and we're going to show you a lot of little stamps of pictures. Actually, could someone turn this light off, or do we need all this light to be on? Okay. And it looks like we are stamp collecting, but cluster survey is not just stamp collecting. One does get some science out of this. And these are what I think are the sort of three primary objectives for doing galaxy cluster survey. One is using cluster as indicator of structure, and allow you to measure cosmological parameters from the point of view of the growth of structure, but also volume, since you're looking at volume density. And obviously, one of the earliest applications of using galaxy clusters to look at galaxy evolution, and especially important in the sense of looking at the effect of environment in galaxy evolution, where you can actually, from the field to the center of cluster, you have a factor of 1,000 at least in cluster density. And this topic is still relatively new, and as you see, that's what we're going to concentrate on, using galaxy cluster basically as gravitational lens telescopes. And you see that when we have a large sample cluster, when we're able to have sufficient number of statistics to do some very interesting work on that. And Mike will mostly talk about how far we are going at this point with the cluster search. Now, when you want to do a galaxy cluster survey, these days, compared to 10, 15, 20 years ago, the objectives are quite a bit more advanced, so that in order to sort of do a useful cluster search, there are several things that you want to keep in mind in designing a survey. And one is that you need very large area. And I think 10 years ago, 100 square degree was big in the sense of searching for high redshift cluster. But nowadays, you might as well go all sky if you are able to. There's only so many square degrees up there. But certainly the order of 1,000, 10 to the third square degree, you find is really a good thing to have if you want to really do all the science properly. High redshift galaxy cluster probably give you the biggest leverage in both galaxy evolution, cosmology, and also in getting lensing sample of sources that are at high redshift. So you really want to find galaxy cluster to as high redshift as you can. And the optical survey that we're doing is designed to go up to about redshift 1. I have two slides about a IRAC survey, which go up to redshift 1.8, which no longer exists in this talk. We're able to use the same method that I'm going to talk about to go to much higher redshift. And secondly, it's all nice and well to say you find a cluster. In order for it to be useful, you need to able to characterize your sample so that people can pick sample and define selection effect, etc. So you can do something that's a little bit more quantitative. And minimally, you need basically distance and mass, which you measure by redshift and some sort of mass proxy whether it's X-ray luminosity, X-ray temperature, optical richness, or Z parameter. And so nowadays, as most of you know, there are sort of three major ways of finding galaxy clusters. They each have their own advantages, and they each have their own disadvantages. And they also have their own selection effect. But that's for totally another subject area. Now, optical cluster search, I would say 10, 15 years ago, is not looked at as a reasonable thing to do for finding high redshift cluster, primarily because of the very large column of galaxies between you and redshift 1, making a galaxy cluster not stand out. But in the last decade or so, there's a real resurgence of using optical survey to find galaxy cluster, primarily because the development of these large aerial detectors, and more importantly is now we are using, basically using multicolor, searching cluster in multicolor space, which allow us to overcome a lot of the projection effect. And in particular, the red sequence cluster survey is the first such large-scale cluster survey trying to find high redshift galaxy cluster using the red sequence of every type galaxies in cluster. So it's a color matching diagram, color matching, and all the early type galaxies will sit in a specific color sequence, elliptical and S0. They're the reddest galaxy at any given time, not counting dust. And so when you have something like this, if you only look at galaxies in a slice of color that you know whether early type galaxies are, you basically get rid of all the background galaxy and all the way around. You get rid of these are all backgrounds, and here some of the clusters, some are in the foreground. But primarily you get rid of some of the foreground. You're right, Mike. You get rid of all the foreground galaxy and most of the background galaxies. And the wonderful thing about this is that you only need 2 filters if that's all you want to do, is to find clusters, which allow you, nowadays when you have this much bigger camera, it's not as big an effect to have only 2 filters, but if your camera is small, having 2 filters is a big advantage. And the K correction of the elliptical galaxy allow you to actually, on a color matching plane, map out the redshift, so give you a very accurate photometric redshift using just 2 filters. So that give you one of the criteria of characterizing your cluster sample. You don't need to go out there and get 10,000 spectra 10,000 galaxy cluster. You're able to get a reasonable photo Z to help you with the sample. And this gives you an example, an early example of the RCS cluster, where if you take a field, a CCD field, you look at all the galaxies in the field up to a certain magnitude. This is your density distribution, and it's hard to pick up a enhancement. But if you only look at a certain color slice, for example, in this case, redshift 0.9, elliptical color slice, you see all the structure here. You pick up the peak, and here's your cluster. And as I said, the red sequence also allows you to pick up the redshift reasonably accurately. So it's photo Z from the red sequence, and here's the spectral Z of a set of measured RCS clusters. For RCS1, we'll talk about the 2 survey in the next few slides. We can get accuracy, get up to 0.04 to 0.08, depending on the redshift. And RCS2, because of better calibration system, we're actually able to get photo Z down to as good as 0.02. So the RCS1, which is basically my thesis while I was in Toronto, image 92 square degree and SCFHD and CTIO using a camera that's 1/3 square degree. And typically we image 2.5 times 2.5 square degree of sky. What we tried to achieve at that time is to measure omega m and sigma 8. When we first started, W was not on the map. And looked at cluster evolution, and in the end, we produced a cluster catalog that have about 7,000 systems in it. Although if you do a reasonable mass cut so that you are very complete and have very few false negative, there's about 1,000 clusters that are useful between sort of redshift 0.3 to 1 for various studies. And when CFHT built a MegaCam, a 1 square degree camera, we started the RCS2 project, which is a 1,000 square degree survey. A little bit shallower than RCS1, but we think we can still go up to Redshift 1 with sort of a several times 10 to the 14, couple of times 10 to the 14 solar mass kind of limit. And you can see that it's very shallow in the sense for a 4-meter telescope, although this is still about 2 matrix deeper than Sloan, and takes about a total of 45 nights to get about 800 square degree, and we should be able to detect, as I said, cluster up to about 5 keV to Redshift 1. This is MegaCam with 9 times 4, 4,500 times 2,000 pixel CCD with this diameter is about 1 degree. The patches that the 1,000 square degree patches we survey are marked in white here with other people's patches somewhere in there. So each patch make up of about either 6 times 6 or 9 times 9 integration of the MegaCam. So each one is 1 square degree, one of this box. And one pointing looks like this with 36 CCD. Each CCD has about 500 to 600 objects detected on it. And this shows you how big the moon is if this is one patch. So when we did RCS1, the goal was to try to get a constraint on Omega M and Sigma 8. And we recently just published a result using RCS1, using about 70 square degree. So this is just a quick, going over quickly, that result just to show that, in fact, galaxy cluster is potentially a system that you can use to get constrained cosmological parameters. And essentially what you do is you measure the number of galaxy clusters as a function of volume, and here's the mass function, and here's the cosmological dependence, and then you have this fudge factor which links the mass observable, whatever you're observing, to the actual mass in the model that you try to fit. And you can see that for galaxy cluster, it doesn't take a lot of signal to noise to separate between omega m of 1 and omega m of 0.3. So even out to redshift 0.5, 0.6, there's a huge difference in the expected number of clusters. And so this is an optical survey, and you want to use some optical parameter to be your mass proxy. And what we use is an optical richness, which is basically a count of galaxy, net count galaxy out to a certain absolute magnitude. And you can see that this is so velocity dispersion, weak lensing mass of cluster with different richness, that there is a reasonable correlation, although the dispersion is different depending on what sample you use. And when you don't know how things are related, you assume it's a power law, so the mass is equal to some power law function of the richness times some constant, and then there's an evolution term thrown in this equation. And we are fitting basically a 7-parameter fit where omega m sigma 8 is what we want to derive. The h and n, the slope of the power initial perturbation is, we use W map higher, and then we have 3 cluster parameter from here where the mass limit at each bin, which is a combination of these 2 parameters, is fitted together. And then we also put in a scatter of the relation in order to model that, and assuming omega total equal 1. And this is the cluster count as a function of redshift, the data, and then this is the fit. And this is what the result look like on a likelihood. And the result that we obtain basically agree with the typical number And it's not so much a measurement of these cosmological parameters, but to show that, in fact, using this kind of self-consistent calibration method between mass and some observable, one is actually able to derive reasonable answers. And RCS2, which is 10 times bigger than RCS1, we hope to be able to provide constraints or the order of this kind of accuracy. This is what Magellan did for the SPT survey, assuming 22,000 cluster. RCS2 probably will have about, 22,000 cluster. RCS2 will probably about 10,000 cluster. So the number would be so comparable. The other interesting we find in RCS1 and probably RCS2 so far is that we actually seem to find many more, or a few very massive structure at high redshift. This is one of the RCS1 cluster with nice strong lens at redshift 0.9. And when you look at the red sequence density map, it looks like this, where this is this little box here. Well, actually, this little box is this little thing here. But this red sequence lump here is this cluster. And one can see two other very large peak, about 3 to 5 megaparsec apart at redshift 0.9. And if you look at it in Chandra X-ray, what you find is that these three peaks correspond to 3 other clusters. And this is actually spectroscopy data using IMACS and Magellan, doing a 27-minute field where we used about 700 slit and got about 400 redshift, of which about 100 all sit at redshift 0.9. And you can see that the 3 X-ray sources are in fact clustered at the same redshift, and the large scale structure being mapped out at redshift 0.9. And if we assume that these 3 clusters will merge together by about redshift 0.5 or so, they will form sort of a about 10 to the 15 solar mass clusters. And David Gilbank, we published a paper with David Gilbank as the first author. We looked through Millennium and body simulation to see how often one would expect to find 3 or several times 10 to 14 solar mass clustered together. And this come out to be the order of a few % chance of seeing that happening. And as I said, we're going to mostly concentrate on strong lensing. RCS1 also was used for weak lensing in the last half dozen years or so. And so this had nothing to do with clusters, but just using this 90 square degree of data on to use weak lensing analysis on it, which is what Hank Hoyster did. It's a serious paper from 2001 to 2005 on both large-scale structure, galaxy biases, and also galaxy lensing halo. And also Simon et al., using the same data, have done a first detection analysis of galaxy lensing, which have just come out. And I'm just going to show a couple of wheel graph highlighting some of the interesting we found using the RCS1 data on galaxy lensing. So for example, we talked about dark halo shape yesterday for cluster, and this is what RCS1 found for galaxies. If you look at the electricity of the dark halo as some function f times the electricity of the lenses, which one can measure from the images, and do the fit, one find that this multiplication factor is of the order of 0.7, 0.8 or so, which makes the average electricity of the halo to be above 0.33, since this is what's measured and this is what's derived from lensing. And you can basically rule out spherical halo, which f equals 0, at a very, very high significance. We have 33 square degree of photo Z, And combining lensing and photo Z, one can say something about these dark matter halos, since you can place them at various distances. So for example, here's a plot of the mass to light ratio, or the mass, virial mass from lensing versus the light that's measured in 3 different bands. Here's the mass to light ratio, and you can see that there is perhaps a general increase at the high mass end. This is some model that I think Feynman Bosch's group had. And this is an attempt at looking at the baryon and stellar mass in these dark halos. So it's the color of the galaxy on this axis, and here is the virial mass versus stellar mass, where the stellar mass is, we have to model that with different IMF, and you get somewhat different answers. And the interesting thing here is that if you separate your galaxy at B minus 0.8, which separate between early type and late type galaxy, and you compute what the virial mass to stellar mass is, you find that there's a factor 2 different. And so this seems to imply that early type galaxy is inefficient in converting baryon into star by about a factor 2 compared to late type, which probably due to the fact that early type galaxies start forming star very early on and they blow all out the gas. And in fact, the red galaxies seem to convert about 1/6 of the baryon into stars, whereas the late type galaxy is more like 1/3. With RCS1, we did a, this is interesting. It doesn't seem to recognize, it's great. We did a strong lensing search in which we just used the survey data, and we found 5 lenses at various redshift, which some of these pictures show. Here's where I don't have lenses of all the pictures, and then we find 3 more lenses in deeper images that were taken at Magellan. And when you look at the statistic and the model that people had in the early 2000s, it seemed that there are a factor of 2 or 3 more strong lenses than one would expect. I think partly, as people think later on, that partly because the modeling of this is not very detailed in the old days, so some of these discrepancy has disappeared, but there still seem to be more strong lenses than one would expect. And having found sort of about more than half a dozen of these lenses in 90 square degree, one would expect one able to find many more of these in the 1,000 square degree survey, and that's what Mike's going to talk about. And when you have a large set of lenses, you can study the source in great detail. This is an example of a Redshift 0.7 cluster producing a multiple lens, where this one's about almost a Redshift 5, it's about 4.9. Most of the light you see is actually from Lyman alpha. And so for example, this is a VLT spectra taken in the early 2000s, where this is the image in R band and I band. We design a curved slit, and you get a Lyman alpha line. Here you can see how most of the light comes from Lyman alpha. This is a Redshift 5 or so, 4.9. And if you do this carefully, then in theory, one will be able to study the dynamics. For example, the velocity dispersion as a function of distance, or resolve velocity dispersion, or resolve velocity themselves. So you can actually look at the dynamic of the system with it widely magnified in space and also in flux. So with this, I'm going to let Mike take over, if Mike's awake, and on what we have found with RCS2 lensing, which will show a very interesting set of strong lenses.
All right. Thank you, Howard. So to focus in specifically on strong lensing, so you have some sense of, we're doing these large cluster surveys, they're well characterized, we understand the cosmological setting, lots of various and sundry supporting data. I'm involved in several large programs to find and characterize strong lenses. And so just to make that clear, there's the RCS1, RCS2 collaborations. I'm involved with a follow-on to Sloan involving roughly these people. And I'm going to talk very briefly also about an instrument that's designed to facilitate understanding these systems. I don't know if this is helping at all, but anyway.
Is it on?
That's a good question. Has it been on? Well, there's a green light,
That's a good sign.
so it's on. So as Howard said, RCS2 is a lot bigger than RCS1. It's roughly 1,000 square degrees. The redshift limit pulls back slightly, basically because above redshift 1 to first order we don't understand clusters at all, and I don't think they're all that useful for cosmological studies at this point, so we purposely pulled the depth back slightly. It's originally a GRZ survey. Another program has added I. We may even eventually add U. So it's sort of Sloan kind of filters, basically, a few magnitudes deeper. And indeed, if you actually count up the total number of objects detected in the images, the total number of objects is comparable to the total number of objects in the photometric sample in Sloan. The primary sample is roughly 200 million individual objects in these images.
Can you say what you mean by we don't understand clusters beyond redshift 1?
Well, tell me what the mass of a cluster is above redshift 1. You can point to 2 or 3 clusters where you have 200 kilosecond X-ray observations where you could actually say this cluster has this mass, and beyond that we don't know much. I mean, if the fundamental thing you need to do cosmology is mass and redshift, actually understanding mass observables above redshift 1, where things probably really start to come apart, we don't have the data to do that robustly right now. We don't understand scatter in mass observables in particular, which is critical to understand. And so we made the tactical decision when we were designing RCS2 to actually not really try and push beyond redshift 1. And it's observationally incredibly expensive to get that data. And we're still at the stage right now in the cluster community where I think we're doing detailed studies of samples of handfuls. And we have to go beyond that before I think those systems become really important. You know, it's true that the SZ surveys will find significant samples of clusters beyond redshift 1. And it's probably true that that as a mass proxy is going to be relatively robust. But you know, ultimately you actually have to go out and make that test. And you make that test by actually looking at multiple mass observables at the same redshift, sort of in situ at those redshifts and trying to understand things. And we're not there yet. So I'm going to talk about some strong lenses pulled out of RCS2. This is pulled out of slightly under 400 square degrees of data, 30-odd thousand clusters out of that area. Most of those, of course, are relatively low mass systems at intermediate redshift, because at redshift 0.3, 0.4, we're really getting down into the group mass scales and finding cluster systems in these kind of data. I'm going to talk about a couple of, well, I'm really going to focus on one sample, but there are multiple sort of strong lens samples you could define out of data like this. I'm really going to talk about sort of bona fide giant arcs. Now, in a survey like this, we have imaging to the same depth over all of the clusters, which is deep enough to find arcs directly. So basically, every potential lens system at the sort of cluster scale has been searched for arcs to this surface brightness limit, okay? And so far in that sort of 400 square degrees, we're talking about 80 new systems, okay? You can also find lots of other things that you look at them in these images and you're pretty certain, yeah, that's a lens of some sort. We haven't looked over all of the images, but around the clusters you often find sort of galaxy scale strong lenses where you have sort of a blue ring around a cluster galaxy. There's probably some boost from the cluster potential there. And there are lots of these. This is very incomplete. We didn't set out to look for these. We haven't done a comprehensive effort to find them. There are hundreds of these things in the data. I'm sure there's also lots more just around random potential lenses out in the field. We haven't looked at them at all. I don't know what the relative scientific utility of putting effort into that is compared to looking at giant arcs. And at some level that has to await some automation of lens finding, because it's just, with this scale of a data set, it's kind of beyond the human eye to do. So just some postage stamps of some of these lenses. The lighting here isn't great, but there's a blue arc there. Somebody in the front can probably see. This one's rather obvious. I'll talk a little bit more about this one later. These are sort of real giant arc systems where the arc is obvious. Yeah, you probably can't see that on this data, but there's a big blue arc there. Okay.
That green thing is that's it's like you painted on it.
Well, that's a cosmic ray.
No.
That's a cosmic ray.
If you go back, what is that green thing?
No, that's just a defect on the chip.
Okay.
These data are kind of dirty.
She was not an asteroid.
Yeah, because if it was, it would have a blue and a red streak beside it too.
Systems don't they?
Yeah, but these data were taken sequentially most of the time, one filter after the other. Not always. This is actually a very large system. This is the main cluster here. There's an arc out here and some other stuff as well. I'll talk about that system later too. You know, this is just a small smattering. If this cluster is actually, so that's an asteroid right there. Various lenses here. This is actually a MACS cluster as well. This is a very strong X-ray source. Just happened to overlap with that. Et cetera, et cetera. Okay, so there's lots of things that look like this. This is sort of these galaxy scale lenses. Okay, people who think about strong lenses are like, it's probably a strong lens. And there's lots of stuff like that. There's stuff that I don't know. Is that a galaxy or a lens? I have no idea. Something bizarre. And there's also tons of this kind of stuff, right, where you have a cluster and kind of tangentially shearish kind of blue thing, kind of a little ways out where you'd expect to see arcs. I don't count stuff like this. I'm not going to talk about any of this stuff. What I'm going to talk about really is things that are easily recognizable giant arc systems, okay?
So, Mike, on galactic scales, did you look at the image? I mean, how much of the images have you inspected by eye?
A very small amount, because we've only really done, this is all found by eye, and we've only looked at places where we said there's a cluster here. So we've probably looked at a few % of all of the survey.
Okay, so
visually.
those happen to be nearby.
And there's, you know, these are all sort of in clusters.
I see, okay.
Okay, so these are sort of cluster members. And so there's, and I think we found, I don't know, 100 of these in that first pass. And we weren't, you know, I'm sure we were not comprehensively looking for things like this. The eye was not trained to find those. So there's probably double that in that area. And I'm sure there's hundreds more in the rest of the survey. So that's RCS2. So right now about 80 giant arc systems in RCS2. I'm also heavily involved in a program following on Sloan where basically we're taking a cluster catalog defined out of Sloan, okay, using the Sloan imaging data to define a cluster catalog in the same way we did in RCS, and then re-imaging those systems in blue filters at the WIN telescope and at the Knot telescope in the Canary Islands to a depth that's very similar to the RCS2 depth to go and look for arcs. Okay, we've re-imaged about 600 massive clusters out of Sloan so far. And from this, we can also define two giant arc samples. One is our so-called blind sample, where we're basically constructing a cluster catalog purely on the basis of sort of observable measures of the clusters in the Sloan catalog, so principally a richness and N-gals, something like that, and just re-imaging those blind. Okay, and the principal goal there is to create a well-defined sample of lenses. We have also, because of systems in RCS2 where the arcs are extraordinarily bright, we realize that there must be systems in Sloan where we can see the arcs directly in the Sloan images. So we've also extended the visual examination process that we've used in RCS2 to the Sloan images and sort of done just a quick visual examination of all the Sloan images and created what we're calling our visual sample. And really the goal there is to capture the brightest arc systems. It's not a complete sample. It's probably not useful for sort of statistical cosmological work, but it does let you find the brightest arcs in the data. Here's some Subaru images of the cores of some of the lenses. So these are much deeper multicolor images than the RCS2 images I showed you before, so don't get fooled. These are sort of comparable systems. But these are from Subaru, actually from weak lensing work. These are just a few of the systems out of the Sloan survey. That's actually Abel 1703, which was first noticed as a lens in the work we were doing. It just happened to be in our sample. This is the highest redshift one in the Sloan sample, redshift 0.67 cluster from the COAD strip. Must be 2 arc minutes for these images. Here's just some examples. These are single filter, not images in G-band, just from a few months ago of some of the arcs from the visual sample. Some of these are really bright. Just page through them here. Some of them are really quite pretty, almost complete. This is actually a Gemini pre-image for some spectroscopy, one of these systems. You know, these kind of arcs are actually visible in the Sloan data. They're sort of G of 20 type things. They're really quite bright. And some of them in the Gemini data look, you know, really pretty. Just to give some context here, lensing and cluster was suggested in the 30s. The first one was found in the 80s. And
It was actually found in 1973.
okay, reported in the literature in the 80s. And not really as an arc, but as an extended, vaguely blue thing that might be due to star formation or shocks. The abstract for that paper is kind of interesting, actually. We published a few at RCS1. Other people have been sort of contributing to this. There's sort of been a growth industry of finding very faint arcs in HST data, which is sort of a little distinct from what I'm talking about. We published some of these Sloan things, and in the last sort of year and a half, this is now mostly unpublished, but we're talking about, we have now a couple of hundred cluster scale strong lenses known, and this is going up at sort of a rate of 40 or 50 every time we go to the telescope now. Okay. So, and when you start talking about things like DAS and pan-stars and LSST, we are going to be in a situation where we have thousands, if not tens of thousands of these systems. So, let me just mention a few science ideas. There's been some ferment in the literature in the last year or two about the fact that there are these clusters with very large Einstein radii, or as Joe Hanawi said, their concentrations are too large. Basically, there's too much mass down in the center of these clusters compared to what you'd expect. This is one of the objects that's cited in this problem, Abel 1703. This is just a recent, again, this is a Gemini pre-image of another one of these systems. This is just from a few weeks ago. This is the principal reason why we looked at this initially. This is a fairly bright arc. This is a Sloan sample, and you see this has many, many other strong lens features. This again is one of these systems where there seems to be too much mass down in the center. And this is actually a figure from a paper by Tom Broadhurst recently. And this is sort of one system they added to this figure, it's Abel 1689, where you can see its Einstein radius is too large for the total mass of the cluster. And for those systems where we have some indication of total mass, either out of RCS2, systems out of RCS2 or the Sloan program, I can sort of, whoop, that's not supposed to happen. Oh well. There was going to be a bunch more points on that plot, and they all lie above that line. This is another system. This is from RCS2 now, RCS 2327. This is a cluster at redshift 0.7, which has an Einstein radius of 50 arcseconds. Okay, for a source at redshift 3, this arc here. This is a very massive cluster. We have a lot of other data, you know, very well measured velocity dispersion, X-ray temperatures, everything else. Even so, it is a very massive cluster, but its Einstein radius is like a factor of 2 too large. Okay. Oh, here we go. This is what I was thinking. So we can make these measurements for clusters where we actually have some indication of total mass, and they're all basically not where you would expect them to be. So something is not quite right.
What are the lines?
Okay, this is a prediction from simulations of the relationship between Einstein radius and halo mass for so-called relaxed clusters, and this is for unrelaxed clusters. Okay, and the sort of error bars on these measurements is something like that.
Have you folded in the triaxial?
Yes, this includes the bias that's inherent in going out and finding strong lenses to begin with, which tend to be more concentrated than average clusters. I believe it's dark matter only. Yeah. So there are a lot of ways out of this. Okay, one of which may be baryon cooling effects, but there's not good agreement right now. Okay. There's also something peculiar in the redshift distribution of the RCS2 survey. It was true in RCS1 as well, but we have much better statistics now, which is that if you look, for example, at the redshift distribution of the lenses, you have too many lenses at too high a redshift. And indeed, you can get some indication of the masses of these things. And what really seems to be happening is we are missing, relatively speaking, low redshift, high mass lenses. Okay? And there is no good selection effect that you can invoke that explains why you would miss those. Those are the easiest clusters to find in a survey. And we do have the occasional system that has giant arcs that is a low redshift, high mass cluster, just relatively speaking to the number of such lenses that are, say, high mass, high redshift systems, or indeed lower mass systems. They're just not as common. The distribution is not what you would expect. For example, if you get very specific and you say, okay, let me restrict these samples to just things with Einstein radii greater than 10 arc seconds, and you measure the median redshift of, so these are sort of massive clusters now, or large Einstein radius clusters anyway, and measure the median redshift of those. So for the Sloan sample, you're talking about a median redshift of 0.41, searching over this redshift range. For RCS2, it's a median of 0.6, basically searching over that redshift range. And your expectation is that it's going to be something more like this, which is not what we see. Is this related to the fact that clusters seem to be more concentrated than we expect? Maybe.
Is that a deficit compared to evolving the high redshift population, or a deficit compared to, for instance, X-ray selected cluster sample data?
I'm not sure I understand your question.
If you go to something like, says, the X-Bats catalog, something like that,
Yeah.
and look for all of the giant arcs in that catalog, are your clusters have fewer, the low redshift massive ones, are there fewer gravitational lenses compared to the X-ray selected catalog?
No,
Or-
because any X-ray selected cluster that exists, we will find quite easily with our tech. Those will all exist in the catalogs. It's just that relative to, so those X-ray samples don't go to as high a redshift
Right.
over these kind of volumes. So they really haven't even probed the parameter space that we're probing here. So, you know, it's my statement is a relative statement internal to this catalog as opposed to in comparison. So the other, of course, thing that these things are great for is looking at very highly magnified background sources. You can learn all sorts of things about the universe you otherwise wouldn't. This is the classic object, CB58. This is a spectrum from Keck of it, which actually Howard discovered this object a little over 10 years ago now. This is this object again at redshift 0.9 that Howard showed. That thing there, for example, is a galaxy at nearly redshift 4, and you can get really rather nice spectra of these systems that you otherwise just couldn't get and learn about the physics of galaxies at high redshift. That source there, for example, around one of these bright arcs from Sloan, that's in a shell spectrum of it. It's several times brighter than CB58. Okay, this object, which I said I would come back to, this is out of RCS2, is so bright that if you actually forget 1973, if you'd known where to look, you could have found it in the 50s on the photographic plates from the Sky survey. Okay, the trick, of course, is knowing where to look. And this thing basically is a big double-arm spiral at redshift 1.7, and you can get a remarkable view of this thing. This is 6 times brighter than CB58. You can start taking the spectra of individual features inside this galaxy from the ground. Okay? So, built an instrument to let you put I'm just going to rush through this. This is sort of typically what you want to do spectroscopy in a big lens. That's how many slits you get. Use an IFU, you get something more like that. We now have an instrument that lets us put down all those slits. There, ask me about it later at coffee. It works. Let me throw these up and let's have a discussion. So, one of the points I really want to make here is that in the last 20 years, up until a few years ago, we had a couple of dozen strong lenses to work with. And every one of them got 20 or 30 orbits of HST time and N nights of large telescope time and this and that and everything else. That just cannot be the way to operate anymore. We have to rethink how to deal with strong lens samples now. We now have hundreds. Okay? In 5 years, we're going to have like 1,000. In 10 years, it's probably going to be 10,000. And this offers some opportunities scientifically, but it requires a real change in how we approach using strong lenses to do science. So this is just some thoughts on what we need to think about and what some of the scientific questions are. I'll stop. which no one's going to respond to.
Yes?
I think the main issue really we're facing is the manpower issue, frankly. And given that we cover this from the point of view of some galaxy scale lenses, you're considering how much effort goes into modeling a single cluster
Right.
in detail, and we still don't know how to do that well. And we probably have maybe 10 clusters that are doing models. I don't know if you
Probably.
yeah,
It could is defined as fitting them to a I-square of 100.
right, exactly, with an RMS cut and 1 arc second or so.
Yeah, and if really good, there's probably just a handful. You know, if you're talking.
There are any, I mean, we've got HST, your astrometric precision is a milliarc second.
Right, right.
No one comes anywhere near.
No one anywhere comes anywhere near the data. That's absolutely true.
Right, so but
You
even-
shouldn't come that close, right? Because it well, if you understood the mass distribution, you challenge the mass distribution. That
Yes.
was a cluster because of our mass systems.
Modeling is an issue, and the number of people who can actually, the number of people who can even construct those models is small.
Right. The large mass distribution,
Explain to me the halo structure of galaxies and clusters. It's barely scratched.
this is like little lumps.
Spoken like a
Anyway,
true.
what I was trying to say that we need probably to come up with more automated methods to model these things, and also really develop a culture of sharing that is starting to exist, but it's not quite there yet.
Yeah, we are completely unready to deal with this kind of thing.
I mean, I think it's overwhelming with the amount of data we're trying to get.
Yeah, and so one of the ways to do this is you say, well, I've got 1,000 lenses. Let me pick the best 10 and take my limited resources and put all those down onto the best 10. But which best 10?
No, but
Does-
it's a
you know.
good approach because you learn a lot from all of these systems.
Yeah, but then you just basically you've exposed yourself to selection functions you don't understand.
But you already selected the best 1,000.
Not in RCS2, actually. We looked at all of them.
I know, but the ones you're going to make mass models of are the ones that succeeded in catching your eye with a nice arc, right? So if you make these mass models, you also better decide what am I going to learn by looking at that.
Right. So you have to close the loop to the point where you've done sort of, so ultimately you're going to go back to a simulation and you're going to make a comparison to predictions in a simulation. You better get to the point where you're actually simulating images that look like the data that you're working with and running your selection process on those images.
Hence the great track record of simulations and predicting the number of arcs.
Right. But this is another thing. So if you're doing a cosmological study, what's the appropriate metric to work with? I mean, what we've done to date in the literature is basically the number of arcs per square degree on the sky. That surely is not the best thing to use, but there's never been an investigation of what is the most appropriate metric to use in the data.
Is the way to do this maybe weak-cleansing? Because I've never heard someone who actually does simulations say we need to go to the simulations, do X and Y, and get strong ones and predictions out. Because the answer you'll get out will be complete garbage, right? And
Well, then the simulations are wrong.
You need to know everything. You need to know everything about the optical appearance of galaxies, and then you need to ray trace it through a highly resolved potential.
Yeah.
And then you need to put it through the whole observing pipeline to figure out whether that would or wouldn't get classified with your scheme or not.
Yeah, it's not easy.
If you have 1,000 of these lenses, I wonder about instead taking the ones you've selected, however you've selected them, doing a weak lensing analysis on them, doing a weak lensing analysis on things you can select uniformly that aren't spectacular, and seeing what the difference is. Right? That might give you a handle on your selection, but you're never going to be able to do it for first principles.
Well, remember, weak lensing measurements of individual cluster masses are not very good.
Well, that's what I'm saying. You need a big sample to be able to stack a lot of these things. But that just strikes me as one way to do the selection. I don't think you can do it from the ground up because of all this details of using something novel as surface brightness.
Well, as an observer, as a telescope jockey, my approach at some level is to say, right, this is the way the universe really looks. And just sort of throw that on the floor and say, go ahead and make your simulations work.
You can't make a simulation of what the universe looks like.
totally naive. Oh, foolish me.
Even if you could, what would you learn from it? Because
Well, you'd learn your simulations were right.
No, you wouldn't. You probably haven't learned anything because in your simulation, you've canceled out a whole series of mistakes you don't know are there to make it look like the Hubble field or whatever. Right? You haven't learned anything. No, I mean, what you want to do is you want to make a simple simulation that doesn't look like the universe, and then you've learned something. But I don't think recreating optical images in a simulation teaches anything.
Okay, I disagree, but let's talk about it at coffee.
Let me ask, is this higher concentration than expected? Does that have anything to do with what Andrew Zentner was talking about yesterday?
I don't know.
I would guess probably. Well, I would say first that I agree with James, basically. From the simulation standpoint, it's just an unachievable goal. I think is what James is saying. That's basically right. But I think probably, I haven't actually done the calculation, but it could have something to do with that, where you're redistributing mass.
People didn't hear me.
I talked about yesterday, redistributing mass and halo on large scale, just due to baryonic effect.
Well, the weak density results was behind the lower concentration.
Yeah, that's
So,
still it's
I have no idea what causes the difference.
You still have 30% wiggle room.
We're consistent in choosing with the theoretical predictions.
So your centroids are
That was an initial worry, but
This also depends on the mass distributed on a much different scale. I mean, that's the big. The simulation that I talked about yesterday only works because I only cared about how the mass is distributed near the virial radius. That whole talk yesterday. If I actually cared about
much further out.
Yeah, if I actually cared about what was happening in the center, then it would have been completely much more complicated.
As far as I know, that doesn't get you around the problem of the redshift distribution of the lenses as well. And I mean, they may be totally two completely disconnected things, but you know, as a first guess, they're probably
another
related.
question is, do we even know how baryons are building up mass? Or can we predict how baryons are building up mass as a function of time? I guess that's not clear.
On clusters, it's fairly clear. No more stars are forming to first order, and it's just gas.
But that's not what happens in simulations unless you force it to be that way. Right?
Well, but that does
Right.
seem
So,
to
yeah,
be what
there's
happens in the
something
real
very
universe.
fundamental that's wrong that we don't understand. I agree with that statement, I guess.
Okay, let's thank Mike again.